Good morning, everyone. Welcome back. We have with us Dr. Madhava Syamlal from QubitSolve. We're going to talk about how QubitSolve is tackling the challenging problem of solving computational fluid dynamic simulations with quantum computing, from understanding the limitations of classical CFD simulations and potentially using quantum algorithms and quantum computing to revolutionize industries like aerospace, automotive, and energy, where CFD is such an integral part in optimizing designs and in minimizing the need for expensive physical prototypes. And I'm very excited to invite Dr. Madhava Syamlal to the program today. Sham is the CEO and founder of QubitSolve, a startup focused on developing quantum solutions for CFD. And he has significantly contributed to CFD theory, numerical techniques in open source commercial software. He's renowned for creating MFix, a widely used multi-phase CFD software. And he has also led many initiatives at the US Department of Energy to develop modeling tools for low carbon energy techniques and a DOE mission critical application code for the first exascale supercomputers. He's a fellow of the American Institute of Chemical Engineers and the American Association of the Advancement of Science. And he has received numerous awards throughout his career, including the R&D 100 Awards, the DOE Secretary's Achievement Honor Award, and the AICHE's 2020 Elsevier PTF Award for Lifetime Achievements. We're very excited to welcome you to the program. Over to you, Sam.
Thank you, Abhinaya, for that kind introduction. And let me share my screen. So thanks for the great introduction. I am very happy to present at this program put together by Humanium and Weiser. I consider this to be a very important program, and so I'm very happy to participate in it. I'm also excited to talk to you all, the next generation of quantum computational scientists. With that, I will talk today about a quantum computing approach that we are taking at QubitSolve. It is a startup. So let me start with our value proposition. This will be when we have solved the problem. So today we are not offering this software, but when we are done, we are developing a quantum CFD solver to address the core computational bottlenecks in simulating turbulent and separated flows. In my presentation, I will talk a little bit about CFD and turbulence. So I'll introduce these concepts to you later on in the presentation. We are using a variational quantum algorithm, which maintains the full CFD data sets on the quantum computer. So that's how we are able to overcome the limitations of classical CFD. Again, I'll explain that later on in my presentation, what that means. And by doing so, we want to solve certain problems that are currently intractable. One example is a large eddy simulation of which is used by industry. One particular example is of takeoff and landing of an aircraft, which has significant economic potential. So that's not possible to do today. So we hope to enable that using quantum CFD. So that's a quick introduction to what we are doing. And in today's presentation, I'm going to do in two parts. The first part, I'm going to quickly introduce CFD to you. So I know that you all have various backgrounds, so I want to kind of bring everybody up to speed with a quick introduction. So it's only a 40-minute talk, so it'll be very, very brief as to what I'm going to say about CFD in my talk. And then I'll motivate the challenge, the problem that we are trying to solve. And in the second part of the presentation, I'll talk about the quantum CFD solution we are pursuing, the approach we are taking, what we have done so far, and what we have learned so far. So that's the quick overview of how I'm going to talk. So let me start by telling you about the applications of CFD. So that's what motivates us to pursue this. CFD is used for predicting fluid flow. It can be a fluid flow around the wing of an aircraft. the blood flow in our arteries. It can be fluid flow in reactors, chemical reactors, or the ocean currents. So these are all scenarios which CFD can be used to do predictive simulations. And by having predictive simulations, then engineers are able to design better aircraft and automobiles, perhaps better medical devices, maybe even plan surgery of arteries or veins in a better way, improve power plant devices so that they are environmentally friendly, and so on and so forth. So there are numerous applications for which CFD is used. At the heart of CFD is the Navier-Stokes equations. CFD turns the laws of physics into predictive simulations of fluid flow. And on this slide, I'm showing the Navier-Stokes equations. This is a set of three equations. The first one is a scalar equation, and the second is a vector equation consisting of three equations. So these four equations form the heart of CFD. For other applications, we might add equations like an energy balance or a species balance, but this is the core, and this is the most challenging part, and this is the most interesting part of CFD. So let me explain what they are. So the first equation is a conservation of mass. So mass is neither created nor destroyed. It's a statement of that, spread out in space and in time. The second set, these are called the momentum equations. This is a conservation of momentum, or you can also think of this as Newton's second law. So what we have on the left-hand side is the acceleration, and on the right-hand side is the force divided by mass. So if you remember Newton's second law, F is equal to ma. So this is a representation of that for a fluid. I'll bring to your attention a couple of terms in this. This, if you can see my laser pointer, so this is the second term on the left-hand side, is called the convection term. This is nonlinear. So you can see this u is multiplied by another u. So this is a nonlinear term. And this is the reason for the instabilities in fluids. And the complexities and beauty of fluid dynamics, the source is this. And on the left-hand side, the last term, you can see it's multiplied by this nu, which is a kinematic viscosity. This makes those fluctuations go away. They make the flow smoother. So if we can solve these field variables, rho, which is the density, and the three velocity components, then we fully describe the fluid flow. And anything else of interest to the engineers can be derived from these solutions. For example, if you're interested in finding the drag, you can calculate that once we know this flow field. So this is distributed in space, and it's also evolving with time. So that's the nature of these fields. Navier-Stokes equations cannot be solved analytically, so we use numerical technique. To solve numerically, what we do is the region of interest, for example, if we are interested in simulating the flow around this jet plane, then we discretize, so that is, we segment the volume around this airplane into small chunks. It is called a grid or a control volume. So that's what is shown in the bottom figure. And the number of grid points, we call this the N grid in my presentation. So we will encounter this value later on, this N grid. So keep that in mind. So that means the total number of grid points in the CFD simulation. And as you can imagine, if you increase the number of grid points, the solution becomes more well-resolved. And if you have fewer number of, if a grid is small, it will be a coarse simulation. So an analogy might be, if you look at this photograph, if you are only interested in learning about the outline of this airplane, then it might be perfectly fine to use a very few number of pixels. But if you want to read this NASA 840, you better have it a very highly resolved with a large number of pixels, a photograph with a large number of pixels. So likewise in CFD, for certain problems, it's okay to have a small n-grid, but certain problems you cannot solve unless you have a very large n-grid. And that leads to some bottlenecks. Let me now introduce another concept to you. So this is called Reynolds number. So remarkably, all fluid flows can be characterized with one single dimensionless number called Reynolds number. And that is shown here, this equation. So Reynolds number consists of three things. So there is an L, which is the characteristic length. So if you look at this picture, I'm showing the flow around a cylinder, and L is the characteristic length of some object which is interacting with the fluid. In this case, this is the cylinder. U is the velocity. So in this case, the characteristic velocity is the upstream, the velocity of the, for example, air or water upstream, it is that value is U. And the third quantity is nu. This is a property of the fluid. So if it is or water or honey or blood, it has different values of nu. And if you combine these three, any flow can be characterized with that single number called Reynolds number. And this is a photograph, actual photograph of flow around a cylinder at Reynolds number 26. And you can see here is a sketch of what happens when the Reynolds number increases in this flow scenario where you have a cylinder and there is a flow around the cylinder. At Reynolds number, very small Reynolds numbers, you can see the flow essentially clings to the cylinder and it does not separate. And when the Reynolds number is 10, you can see the flow separates and it forms these eddy currents behind the cylinder. And when it goes up, this detaches and it becomes what's called a von Karman vortex street. But when Reynolds number exceeds about 500, this becomes turbulent. So it's no longer very smooth flow. It is very chaotic. That's what is shown by these doodles here. So the Reynolds number is a ratio of what's called the inertial forces and the viscous forces. Inertial forces are the ones which, as I showed you earlier, the nonlinear term, the convection. So if you, for example, if you push a shopping cart and leave it, it'll keep moving for a while, right? That's the inertia. It will stop eventually because there is a friction which is stopping it. So that's the balance between inertia and friction, and that's captured. So fluids have, and internally there is a friction between layers of fluid, and that is captured by this quantity nu. And the ratio determines whether the flow is turbulent or laminar. So this has been known for a long time. It's even at the time of Leonardo da Vinci, and that's what I'm showing on this slide. So we all know da Vinci as this genius who painted Mona Lisa and Last Supper. But da Vinci was also a great scientist and a great fluid dynamicist. So throughout his career, he was fascinated by fluid flow, wind flow, air flow, blood flow. He was fascinated with all of them. And he was even more fascinated by the swirling flow, the swirls that occur when fluid flows. And he, in fact, discovered how our aortic valve works. He explained very correctly that the valve in aorta that prevents blood from flowing back into the heart is because of the swirling flow of blood in the aorta. And this fact was not known for 450 years after he wrote about it. Even in 1960s, heart specialists used to think that the valve is closing because it's acting like a check valve. Only then they realized that is not the correct explanation. In fact, Da Vinci was correct. It's the swirling flow of the blood that closes the valve. So in this diagram, again, he is showing a beautiful picture of swirling. So here is a pipe from which water is flowing into a tank. And he's showing all these swirls that forms. So there are these big swirls that break up into smaller swirls, smaller and smaller swirls. And that's the essence of turbulence. And when you have very small swirls, it becomes computationally difficult to model those flow scenarios. So let me give you an example. So many turbulent flows are intractable. And here is an example of a car moving at 70 miles per hour. And we can calculate what it takes to do this, to simulate this accurately. So here, the characteristic length, I'm using that as, if you kind of take an analogy with the cylinder, it's this 1.7 meters, that is the height. We know the velocity is 70 miles per hour, 31 meters per second. The nu of air, in this case, the fluid is air, is this quantity. From here, you can calculate the Reynolds number is over 3 million, and you already know that this will be a very turbulent flow. And in 1940s, Andrei Kolmogorov, a Russian mathematician, discovered these scaling laws, and he found out from scaling arguments that the smallest size of those eddies, so the smallest swirling flows, that ratio is Reynolds number to the power 3/4. And in a CFD simulation, if you want a grid resolution, which is of that order, we need to cube it. So there are three sides to it. And that becomes Reynolds number to the power 9/4. And for the given this 3 million plus Reynolds number, we can calculate the number of grid points as 500 trillion. And for a particular D3Q9 CFD method, this will require 81 petabytes of storage. And compare that with the 9.2 petabytes available on Frontier, which was the fastest supercomputer until June of 2024. So now you get the picture. This becomes a very challenging thing to do. And here is a picture of what happens in turbulence. So here we have this large eddy. So this is like the pipe in Leonardo da Vinci's picture, feeding the energy into the fluid, and the fluid swirls around. This picture is a little too neat. Turbulence is more chaotic, but you get the picture. So this feeds energy into these swirls, and these swirls feed energy into smaller swirls, and it keeps on going until the swirls become so small that the viscosity can stabilize that. So, and essentially that energy then becomes heat. So that is called the turbulence energy cascade. And the simulation that I mentioned in the previous slide is called DNS, or direct numerical simulation, where we resolve up to the smallest eddy. And this is impossible to do. So this is for practical applications, it is impossible to do. So most engineers, what they do is something called Reynolds average Navier-Stokes. So you can take the Navier-Stokes equation, average it, and use that for CFD. But averaging then requires some modeling. Some things that you threw out because of averaging should need to be brought back through modeling. So that depends, flow dependent. And as you can again imagine, this will not work for all flows. So people have come up with other techniques where you model only part of the flow, the rest are resolved. So that's called large eddy simulation. And this is industrially practiced, but even LES, sometimes it is impossible to do. So that's, I can conclude this section with this challenge. So the RANS models are not capable of accurately predicting separated flows, whereas LES can predict those flows, but it requires immense computing power, which is currently intractable for certain types of problems. Some problems you can do. So for instance, the airflow around an aircraft during takeoff and landing, those are crucial moments for safety, is an intractable task. And this is identified in the NASA Vision 2030 report. So that's the challenge. And now I'm going to talk about our quantum solution. So Abhinaya, if you have few questions about what I already talked about, I can answer them, or we can wait till the end of the presentation.
That sounds good to me. We do have a few questions on Discord. I can read them out to you.
Okay.
Okay. So this is from Mac from Canada. What are the impacts of the errors accumulated and the time saved or lost from having to use numeric computation? How does inexact sciences further justify numeric computation?
Oh, okay, that's a great question. Yeah, so that's typically CFD engineers worry about that a lot. What they typically do is you do a series of CFD calculations at various grid resolution. Well, first of all, we need to have a numerical technique that is usually second order accurate. That's what we shoot for. Second order accuracy will decrease the error by as a square when we increase the number of grids. So you can increase the number of grids, see whether the solution changed, and that gives confidence in the application that they're doing. Of course, this is not possible all the time. So typically what is done is if you're solving a class of problems, you at least do that for one or two of them to make sure that you understand what are the errors. Then there are other ways. There are very detailed ways of ascertaining the uncertainty. That's a whole branch of computational science called uncertainty quantification, where you track every little uncertainty. It's not only in the numerical computation, but also coming from the initial conditions, coming from the uncertainty in the physical properties, and so on and so forth. And you can actually, in the end, you can make a prediction, and you can also say, I have 95% confidence that this is going to fall in this particular band. So there are various techniques like that.
Thank you. We have a question from Ron from Chicago. Is there any way to predict what the efficiency of increasing the size of the computational grid will be? Or is this a fractal-like phenomenon?
Okay, so when you increase the number of grid points, you are increasing the accuracy of the solution. Efficiency is a different question, right? Efficiency, if I understand correctly, is the computational speed. The computational the expense will go up, and later on I have a slide where I talk about that, and that is typically on the order of n grid, the number of grid points. So it scales linearly with the number of grid points.
Okay, thank you. Last question. So this is from Sujal from India. Could you please explain how is grid points equal to Reynolds number to the power of 9/4 if the grid size is equal to the size of the smallest eddy?
Okay, well, yeah, so that formula, I don't have the time to explain that. That formula comes from Kolmogorow's Kolmogorov theory. So I can maybe very quickly explain, what he did is he looked at the energy balance, and then he said that the smallest eddies are the ones which dissipate. That means the Reynolds number there should be very small. So he said that when Reynolds number is equal to 1, that will roughly correspond to the size of the smallest eddy, so that the inertia is canceled by the fluid flow. So these are all based on statistical arguments, but they have been empirically validated. So was there a second part to that question, or that was it?
No, that's it.
Okay, all right.
Yeah, thank you. We can keep going.
Okay, thanks, Vinaya. So let me now move on to describing what the approach that we are taking at QubitSolve to address that challenge. So we are essentially, as you all know, that we are going to leverage quantum computing to address that challenge that I mentioned in the previous slide. So here, there are many choices that we need to make. So I will explain what they are and why we chose. The first thing we need to choose is the base CFD method. And for that, we chose something called lattice-Boltzmann method. There are two dominant CFD approaches, especially in the commercial CFD software. One is called finite volume method. In this method, what you do is, I showed you how the the space around that aircraft is broken into segments. You can integrate Navier-Stokes equations in each of those control volumes, and through integration, you can come up with a set of nonlinear equations. Then that you can convert into linear equations, and you can solve. This method has this excellent property that will conserve quantities on a global basis, even on a very coarse grid. So this is very widely used. In fact, I think the most widely used CFD technique in commercial software is FDM. The second method is called Lattice-Boltzmann method. This is also used in commercial software, but to a lesser extent. In LBM, instead of solving Navier-Stokes, you solve Boltzmann equation on a lattice, and it can be shown that when the Mach number, that the speed of sound, the flow velocity divided by the speed of sound is very small, it will converge to the Navier-Stokes solution. It's almost like a magic that, how does it happen? So it is not a magic, it is math, but to me, it looks like a magic. So these are the two methods. We chose LBM as our base. And why? Because LBM has quantum parallelism friendly features, and I'll explain what they are. First of all, it'll convert the Navier-Stokes nonlinearity. Remember, I showed you the convection term U times du dx. So that has nonlinearity, but also it has this dependence on values in the neighboring nodes because of the gradient term du dx. LBM converts that into a local form. All nonlinear calculations are located in one grid point. You don't need any information from the neighbors. So that's suitable for quantum parallelization. Secondly, the convection also, to discretize the convection term, there is also a flow direction dependence. So in FVM, when you calculate the convection terms, you will do one thing if the flow is going from east to west, and you'll do another thing if it is going west to east. So depending upon the direction, the values you choose will differ. In LBM, there is no such problem. There is something equivalent to convection in LBM called streaming, and streaming is fixed. So later on, I'll show you that the LBM requires what are called the distribution functions, and there are F0, F1, F2, so on and so forth. F0 will always stay at the lattice point. It will not move. F1 will always move in the east direction by one cell. F2 will always move in the north direction by one cell. F3 will always move west direction by one cell. So it's fixed. So there is no need for any decision as you're streaming. So this is a great advantage for quantum parallelism. And the third one is, I mentioned already that we want second order accuracy. So this is something that CFD folks always look for. And there are many ways to do that in FVM, but all of them involve what are called nonlinear limiters. There are some decisions that you need to make in a nonlinear fashion. So in LBM, you don't need that. Second order comes by the formulation itself. There is no need for any nonlinear limiter. So these are all advantages. Of course, there are disadvantages. It's a low Mach number solution, so it's only for incompressible flow. But there are many practical applications for incompressible flows, including aeroacoustics, which is of great interest to the automotive and the aerospace companies. It demands more memory. The basic Navier-Stokes I showed you earlier, there were only 4 quantities, right? Density and 3 velocity components. In an equivalent LBM, would require 19 or 27 variables, depending upon the model that you choose. So you can see a very huge increase in the number of variables that you need to track. But on quantum computer, that's not a big deal. By adding a few extra qubits, we can easily handle that. Now let's look at the challenges of quantum CFD. So there are three core challenges. One is quantum systems are linear, whereas fluid dynamics is nonlinear. So you need to handle that. The second challenge is the initial state preparation and the final data readout. Those are very expensive on quantum computers, so you must handle that. And the third one is the current state of quantum computers are such that they are noisy and error prone. So we need to have an approach to overcome that. Out of these, we focused on tackling the first challenge. So tackling the challenge of nonlinearities until now. And the reason is this is particular to CFD. There is, other than the CFD developers, nobody else is going to solve this for us, right? So we need to take care of this part. And the noise challenge somewhat comes as a bonus because the techniques that we use also handle the noise challenges. Number two is a general issue with all quantum computing projects. And so many smart people are looking into that and they have developed solutions. So we can adopt that. And we are going to do that soon. So our focus is on tackling the CFD nonlinearity. And there are many approaches for doing that. I'm summarizing that into these four quantities here. There is this excellent review paper by Bharadwaj and Srinivasan. They go through all this and describe in great details the approaches for handling, doing quantum CFD. So the first approach is to use what are called quantum linear solvers. So you might have already heard HHL, and there are other algorithms that can do exponentially fast solution of linear equation systems. And this is very nice because in CFD, ultimately you solve a set of linear equations. FVM, you start with discretization, produce a set of nonlinear algebraic equations, and through some techniques like iteration, you finally produce a set of linear equations. And solving that takes about 75% of the effort. So it seems very appealing to replace that step with a quantum solver, linear equation solver. But this has the downside that the linear equation set is still built on a classical computer. So all the bottlenecks that classical computer has are still there. And also, even if you ignore all other problems with quantum linear solvers, the ultimate gain will be less than a factor of 4 because about 1/4 of the effort is in building those linear equation sets. The second approach is called Coleman linearization. Here, what you do is wherever you encounter a nonlinear term, you replace it with a new independent variable, dependent variable. And then you write another evolution equation for that variable, and that will produce another nonlinear term. And you keep on going. You can replace this nonlinear equation by an infinite set of linear equations. So this is also being tried by many projects. But in this case, the circuit depth becomes very large, and then it becomes impossible to do these calculations on today's hardware. And then there are reformulation of Navier-Stokes, like solving Liouville equation or the hydrodynamic Schrodinger equation. So these are all being tried, but the practicality of these methods is uncertain. So our approach has been to use variational quantum algorithms. And you have already, I know that you have already heard about this in previous lectures. What it does is it translates the fluid dynamic calculation into an optimization problem. I'll explain what that is fairly soon. It can handle nonlinearities. It's still not easy, but there is a way forward, and it's suitable for today's hardware. It has challenges. There are no performance guarantees, unlike other quantum algorithms. You cannot predict a priori whether an exponential speedup is achievable or not. You can estimate, but you have to ultimately prove that empirically, not through analysis. And there's something called a parameterized quantum circuit the design of that is critical for the success of this approach. And the optimizer convergence is still an open problem. We don't know whether the optimizer will ultimately converge for very large problems. So these are problems that need to be tackled. So let me now explain how we use VQA. So as I mentioned already, it's the most promising approach for the near-term quantum computers. And if you're interested, there is this excellent review by Professor Yaksha that talks about variational quantum approaches for CFD. In this approach, we translate solving fluid flow equations into minimizing a cost function. The determination of cost function is now a critical piece that we need to do. And this cost function is parameterized by this set of parameters. I'll soon explain what they are. And theta is a set of parameters in the parameterized quantum circuit. Lambda are normalizing parameters. Then the cost function is minimized on a hybrid quantum classical system. The quantum computation determines the cost function, and the classical optimizer determines the parameter set that will minimize the cost function. And when we converge, we get this solution. So the solution will look like this. It's a set of parameters and a parameterized quantum circuit that can convert these parameters into a quantum state. So that's how the solution will look like. We still don't have the CFD solution on the classical machine, but that's for another day. But at least, if you are successful, we do have a CFD solution on the quantum machine. So here's the journey from classical CFD to variational quantum CFD, which is the quantum approach. So in CFD, as I mentioned before, we want to evolve these fields of density and 3 velocity components at time level n to time level n plus 1. So we'll start from 0, and then we'll keep marching until the time, the end time, which is prescribed beforehand. And in our approach, we are first converting that using lattice-Boltzmann method. And in this method, we convert this CFD field variables into distribution functions. So so this V indicates the number of the distribution functions. So this can vary depending upon what is called the velocity set in LBM. The test that we have done so far is called D2Q9. So that stands for 2 dimensions. So 2 spatial dimensions and 9 velocities. So that is the 9. So F will go from F0 to F8. And now the evolution is taking F from time step n to time step n plus 1. So up to now is classical CFD. And here comes the quantum CFD, where we first convert this distribution functions into quantum states. They are parameterized by theta and normalized by lambda. And now is again the evolution from time step n to time step n plus 1. And ultimately, this is the solution process. You start with a set of parameters known at time step n, and then from that, you predict the parameters at n plus 1. And right away, there is a saving in the space. So the space complexity of this is order n grid for the classical, and for the quantum CFD, it's order log n grid. So you can right away see that the memory bottleneck we can solve with this approach. Of course, that doesn't mean that we can solve the problem, but at least that memory bottleneck is solved. So here are the steps. First, we represent the distribution function FV using a quantum state. So we need to normalize that with the 2 norm of this vector. So V is the number that denotes the distribution function. As I mentioned, in the test that we did was going from F0 to F8. And K is the lattice point or the grid point. So you discretize the space into many n grid points, and you can label those points by a integer k. So K stands for that. And then we represent this field using amplitude encoding, which I'm sure you're already familiar with this. State representation of the discretized distribution function, where K is the kth computational basis state, which identifies the label for that grid point. Second, we need to have a parameterized quantum circuit for creating a quantum state from a state of 0 qubits. And that's what's shown here, where this V theta, which is a trainable gate sequence, is called a parameterized quantum circuit. Here is an example taken from the literature. This is not what we used in our work, but this is just to give you an example. Here, this circuit takes zeros as input and produces the desired field as the output. And what it requires is a bunch of rotations, and each rotation gate is parameterized by a theta. And crucially, here we need the size of theta to be of the order log n grid. Okay, there is no guarantee here, but that's what we require. And if we are able to design a PQC that satisfies this, then we are in good shape. Next, now we have the quantum states. We can translate our classical evolution equation into this evolution equation for the quantum state. And I mentioned the cost function that needs to be minimized. That is a true norm of the residuals of this Lattice-Boltzmann method. A residual is simply if you take this right-hand side to the left, it will be a 0 here. If you use a trial value, it will not be 0. That's called a residual. And the true norm of that is the cost function. I'm not going into the details of that cost function, but here is finally, this is how the solution is done. Here is at every time step, this is what the algorithm does. It has as input this theta and lambda from time step n. So this is known. And in this algorithm is taking that to time step n+1 for both theta and lambda. And it is done using hybrid calculations. So there is a quantum computer which deals with certain things that is shown in this green box above. And there is a classical computer which does some other tasks that is shown in this gold box below. So let's see what the quantum computer does. So it takes this theta values from previous time step, and using the parameterized quantum circuit, it creates this quantum state of the distribution function at time step n. Then this also receives trial values. We don't yet know the final values, but it knows the trial values of theta given by the optimizer. And from the trial values, you can compute the trial values of the quantum state at time step n+1. And from these, this is of course highly simplified. You can compute what are called multi-products. So these are like inner products. And these multi-products are fed to the classical computer. Classical computer already has these lambdas from previous time steps, and the optimizer gives trial values of lambda at the new time step. Combining these, the classical computer can calculate the cost function, and from the cost function, the optimizer can minimize that by adjusting thetas and lambdas. And when it reaches the minimum, we get the solution. So that's the overall picture. And one thing I'll point out here is I'm also showing the data set size here. So I have colored and made the size of the arrows corresponding to the size of the data set. So green thick arrows of order n grid, blue is order log n grid, and the blacks are order 1. That means it is independent of n grid. So one thing I want to call your attention to is these green arrows only live on the quantum computer. So it's never seen on the classical computer. So that's what it gives the advantage of overcoming the memory bottleneck. Okay, so now that's how we do it. And now I'm going to tell you about what we found. So one thing is that using VQA, we can readily see that the space complexity problem is solved. We only need log n grid qubits, and those are readily available even on today's quantum computers, but definitely in the next few years, they're available for fairly large CFD problems. We estimated, again, it's not a rigorous time complexity analysis, but we estimated it, the simulation time scales as log square of n grid. Similarly, we can, for the classical CFD, it scales a order n grid. And this right away gives this advantage. Order log square n grid versus order n grid, meaning the speed up, the quantum speed up rapidly improves with problem size. And for very large sizes, the quantum computing will beat classical CFD. We implemented our algorithm in a software prototype and we verified its accuracy. And now that we implemented it, we are able to do some performance modeling. So it was impossible to run this entire thing on a quantum classical computer. So we came out with a method to estimate the performance. And you can read that this was presented at the AAAA conference, and it's there in the proceedings and in the archive. So you can read about what was done there. We collected data on IBM and IonQ quantum computers, and the predicted scaling comes fairly close to the heuristic analysis of log square n grid. So here we get log cube, not that much off. And then we modeled what will a fast classical computer will do for the classical CFD. And for that, we chose Frontier. It was the fastest supercomputer when we wrote this paper before June 2024. And here the predicted scaling varies with problem size. For small sizes, it was a sublinear scaling. And for large problem sizes, it was a quadratic scaling. So the performance models are consistent with asymptotic scaling, but they also enabled us now to estimate the constant factor cost, which is a very elusive concept, right? Just having a scale up is not enough. We have to be concerned about the constant factor cost. So with the performance model, we were able to predict that. And for our implementation, we found that to be very, very slow compared to the classical CFD. And this is at a particular CFD grid size. So we chose 50 million grid points as the place where we want to compare the two, because this is the median size that is used in typical industrial CFD simulation. So if we can beat classical at this point, it becomes useful for many industrial problems, and then it can solve currently intractable CFD problems. That's why we chose this as the crossover point. And we call this factor Q5E7. So this is a tangible benchmark we will use to track our progress. When this factor is less than or equal to 1, we achieve quantum advantage. And we have identified a strategy to reduce this factor dramatically in our implementation. And we are currently working on implementing that strategy. And if we are successful, then quantum CFD could outperform classical CFD. And in summary, QubitSolve has developed a quantum CFD algorithm, implemented that in a software prototype. We conducted performance measurements on actual quantum hardware. And based on that, we recognized that there is a room for significant improvement. Our algorithm performance improvements, it requires performance improvement to address industrial scale problems. So we are currently working on that, a suite of identified methods and this gives us strong optimism of achieving this goal of being able to beat the classical CFD. And also on that note, I want to tell you that we are soon hiring. So we expect to post something in late August, and welcome all of you to visit our website sometime around that time for details. I want to acknowledge funding from NSF and grants for computer usage at Oak Ridge National